which lives a little while, very little while, and then decays through another process to 2 photons, 2 light particles. And it's the photons that are measured, and the fact that you have this little bump is a sign that there was this little Higgs boson briefly there. Right? That's the signal. But in these cases, and as in all other sciences, there is also a lot of background. There's a lot of other particles that we know that decay to photons and that are not so interesting. We need to fish, they needed to fish that very faint signal of the Higgs decaying to 2 photons out from all those backgrounds, and they managed brilliantly. This is not like looking for a needle in a haystack, it's looking for a needle in 10,000 haystacks. So diagrams, all of which have a Higgs boson here at the end, and stuff happening in front to make the Higgs boson. I'll come back to that a little while later. What this shows is that there are various ways Higgs bosons can be produced in collisions at the Large Hadron Collider in CERN. That's what caused those bumps. So that led to, as I said, a lot of emotion. These are some pictures of that day of various important people. These are the 2 people who presented the 2 experiments, Fabiola Gianotti from CERN and Joe Incandela, sorry, from Atlas, Joe Incandela from CMS. Fabiola Gianotti is now the Director General of CERN. And these 2 elderly gentlemen, this is Peter Higgs, after whom the particle is named. And this here is François Anglaire from Belgium, who also, it is what it is, right? We have to live with it. That's nature telling us that particle is this heavy. Also remarkable, I found, that this is the first time that Anglaire and Higgs met. There were 80 at the time. Now, if you look how much people travel these days and meet each other in this business, it's almost very strange they never met, which is mostly due to Peter Higgs. He didn't travel much at all. He had to always be lured to places away from home, and this seemed to be a very good occasion to do so. But then as soon as you see the bump, and you think, this could be the Higgs boson, you ask, is it the one that we expected? Or is it maybe another one? If it is, what we've really done here, and that's an important concept to remember, is that we've knocked a particle out of the vacuum, which is a strange concept, but I'll illustrate that a bit more later in this talk. So it is really a very, very special particle. And why is the Higgs boson so special then? Why do we devote all this time to it? Well, as I said, it is really a nugget of vacuum. It is the only elementary particle without a quantity called spin. All other particles spin around their own axis in very precise quantities, in either a half or 1 or more. But it's the only elementary particle without spin we've ever seen. So that's already very, very special. But that's not the only reason. It is part of the mechanism by which other particles get their mass. And the notion of mass is an important one. We'll come back to that in this talk. And it's not just something, it also opens the door, possibly, to even more spectacular new discoveries in the future. And that I will address at the end of the talk. These are some pretty significant statements. And I'd like to see if we can understand them a bit better. And for that, we need to start looking at the standard model of particle physics. So let's look at this standard model. And to go for the standard model, we need to not go wide, not look at the cosmos, the macrocosmos, but rather go deep, go inside, go to smaller and smaller distances to the microcosmos. So how do we look to the micro world typically? Well, if you're a biologist or early biologist, you would look at bacteria through an optical microscope. Right? You've all done that, seen bacteria, some yogurt or something. If you want to look at smaller stuff like pollen from flowers or trees, you look at electron microscope, where the particles with which you create the image are not photons but electrons. If you want to go really small, you're using 35 xenon atoms on a substrate. But it picked up 1 atom at a time and put it down for their own smallest advertisement. Very impressive. But for us, that's way too big. That is still way too big, because atoms are like this, right? This is the picture you all know. You have a nucleus and electrons swirling around it. But it really should be a dot that you cannot see. But inside this atom is a cluster of particles called protons. And the scale here is about 10 to the minus 15 meters, so 0 point and then 15 zeros, 1 meter. That's still too big. What we're looking at is 1,000 times smaller than this. And what the standard model allows it to do is to do quantum physics at that scale. So if you've all had courses in quantum mechanics at some point, or some of you know about wave functions and uncertainties, but that's typically with things at the scale of atoms. When you go to such small distances, you need to upgrade your quantum description to something called quantum field theory, and that is what the standard model is. So let's look a bit more detail at the standard model then. These particles, standard model consists of a fairly limited set of particles. Here there are a set of particles that we call quarks, and they have names up, charm, top, down, strange, bottom, for historical reasons. And here are sort of mirror particles called leptons. Here is the electron, well known, and a few others. Neutrinos are here. And here are some force particles, the photon, the gluon, and two others. And here is a ghostly presence in the middle, is the Higgs boson. So it's a famous picture. You've seen it, no doubt, many times in websites and talks. It's nice, but it really is a bit superficial. Right? It really doesn't tell you anything about the standard model. I want to tell you a bit more what's behind this cartoonish picture. This is what is responsible for light, for electricity, for atoms again. The weak nuclear force, that's a force that only acts very short range, but is important for the sun to burn, so rather fundamental. And the strong nuclear force is the force that keeps the protons and neutrons together in the nucleus. If you wouldn't have it, they would fall apart, we wouldn't be here. Interaction. So electromagnetism is about 100. Two particles interacting with a strength of about 100. The same for the weak nuclear force. The strong nuclear force interacts a bit stronger. 0.1 is a typical strength, but gravity 10 to the minus 41. That's much, much weaker, right? So we can ignore gravity for these small particles. That's what we do. Now, why is force a particle? And I always found this picture, even though it's not a movie, but it illustrates the idea. Force is nothing but quantum particle exchange. So here are two people on roller skates standing initially close together, having a very heavy ball that they start throwing back and forth. And you know what's going to happen. They're going to be drifting apart on their roller skates. So particles, they don't push against each other, they just exchange a particle and thereby exert a force on each other. Same thing in the quantum world. It's a pity I cannot find the picture, but I think you can imagine how it works. So that's a very rough description of matter and force in the standard model. How does the Higgs boson fit into all this? Well, a bit with difficulty, because the Higgs boson has spin 0. It does not spin around its axis. It turns out all force particles spin around their axis with strength 1. So it's not a force particle in that sense. It's not a matter particle either, because those are particles that spin around their own axis with strength 1/2, all of them. So it is a category of itself. And what it has to do with is the symmetry breaking of the vacuum. That's a very abstract statement. I'll try and explain it to you. And as a consequence, the generation of particle mass. And that's sort of the next part of the story, the idea of mass. So let's think about the concept of mass. What does mass mean? Mass has evolved over time as a concept. And the reason for that we're looking at this now is very soon after the discovery of the Higgs. It's so important for the concept of mass that Englert and Higgs got the Nobel Prize the year afterwards. It's seldom, if ever, awarded this quickly. You usually have to wait for 80 years, but they got it the next year. Well, their advanced age was also a factor, I guess. By the way, they're still alive, so they could have waited a bit. Robert Brout, he was also part of the paper with Englert. He passed away. He would have been part of the Nobel Prize had he been alive. But let's also not forget Higgs boson has a second word, boson. That's named after brilliant Indian physicist Satyendra Nath Bose, who thought of this statistics of particles with integer spin. So he is also appropriately honored by the word boson. And what did they get the Nobel Prize for the notion that particle mass is associated with broken symmetry, which is for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles. Okay, clear enough? Maybe not. By the way, these are the headings of the two papers for which they got the Nobel Prize for. This is Higgs, and this is Engler and Brout. This is from October, and this is from August, but he was a bit earlier, actually. The first version of this paper was sent in earlier, so they both got it. Also interesting for me is this is the year of my birth. This is just after my birthday, actual birthday, that they published this. So the idea of a light mass by a given force. Also already from the days of Newton, mass as a gravitational charge. The strength with which gravity couples to a mass, to a planet, or to a moon, or to us, is proportional to the mass of the Earth and of the moon, for example, with some universal constant. So these are two different, could happen to be the same, that's been checked, but it is different idea behind the notion of mass. But these are still very familiar to you, I imagine. They wouldn't be weird. So in both cases, it's classical because mass is conserved. When something has a mass, it just has that mass and that's it. Cannot change it. But then Einstein came along in the early part of the last century. He said, no, mass is E over c squared. You know that formula too, I imagine. So this formula really says, no, mass is condensed energy, or it's equivalent to. So for example, if you look at a proton, it consists of 2 up quarks and 1 down quark. The mass of the proton is 938 units. The mass of these up and down quarks is about 10. So you see, it doesn't add up. Most of the mass of the proton, and thereby of us, is made out of binding energy. The energy that binds these quarks. Now, you had 100 years to get 117 years to get familiar with it. Now we come to a bit more abstract kind of mass. So let me take you through that. So this is mass through spontaneous symmetry breaking. This is fancy words for phenomena I'll talk about now. It came actually first, not in particle physics, but in condensed matter physics in the theory of superconductivity. You know what superconductivity is? This is when you make a metal so cold that the electrical resistance becomes 0. Not small, but really, really 0. So, and the explanation of that had to do with this broken symmetry. So this is a lattice of atoms, and you see here 2 electrons bouncing around the lattice of atoms, and what happens is that they start feeling each other indirectly through the lattice and form a sort of bound state. This is called a Cooper pair. It's a bit odd because these have the same charge, but nevertheless they form this bound state. So the lowest energy state configuration of this superconductor is not an empty lattice, but one full of these Cooper pairs. Not empty. Vacuum here is not empty. The word vacuum means empty. It's just a misnomer. It's something that is not empty. Top of a superconductor. This is very, very cold. It's superconducting. You see it floats in the air. Now this is a phenomenon of superconductivity you may not be that familiar with. It has nothing to do with the current. What happens is this is a magnet that has magnetic field lines going through it, and the field lines want to go inside the superconductor. And normally it wouldn't be a problem. If I put it on the table, no problem. But first introduce you what symmetry is if you don't think about it. Symmetry is really for us, you transform something, see if it looks the same. This is a sphere, if you can see it. I can say, well, it's a sphere, then be done with it. I could also tell you, I have an object, and whichever way I transform it, it will look the same. That's a very, and also a Higgs boson field. And how do the electron, they're not 2 different electrons. 2 different electrons here and in the Andromeda cloud, it's just 2 different excitations of the same electron field throughout the universe. Final concept is something called the potential and the ground state. In physics, all systems have what is called a potential function. And it is a quantity which the system seeks to minimize. So for example, if you have a ball in such a conical vessel, then you can have it spin around up here, but eventually it will settle itself into the bottom here. So the system of ball and vessel seeks a situation where the ball is in the bottom. But it's more general than that. Also, for example, the disturbance in a pond, here ripples, they will be there for a little while. At the end, if nothing else happens, it will be a perfectly smooth surface of a pond of water. That's also the ground state of that system. That also happens in lives in such a potential function. It has this little bump in the middle, like the bottom of a wine bottle or many other bottles. And early in the universe, the Higgs field was in a position to be nicely in the middle of this, so very symmetrical point. If you look from the top, you see the Higgs field sitting right in the center. But it is not the ground state. The ground state is this ring of minima. As the universe cools, the Higgs field settles somewhere along the ring. And on the x-axis here is actually the strength of the Higgs field. So if the Higgs field would be comfortable here, it would have zero strength. Throughout the universe, there would be no Higgs field present. But given this shape, the Higgs field is actually here. So there's always a constant Higgs field present everywhere. You can really tell. If you rotate it, it will be somewhere else. This is a broken symmetry. This is a broken symmetry we're talking about. So throughout the universe, there's a constant Higgs field. And here, imagine a particle flying, constantly feeling the Higgs field. And what that does to the particle is it slows it down below light speed. That's the same as having a mass. It's a bit like walking through water. Right? You can run fast, but if you have to do it in water, you go slower because water is pulling at you. These are elementary particles being pulled at by this constant Higgs field and thereby getting a mass. That's the idea. So that's how broken symmetry, which led to this Higgs field, causes mass. Hope that's the story of the Higgs boson and why it's so important. So in a sense, and in a sort of nice poetic sense, the universe is like a cosmic superconductor. Think about that. It's a nice image to have in mind. Okay. So having hopefully digested that a little bit, let's now go a bit to the place where the discovery was made, and it's worthwhile highlighting that a little bit, the CERN, the lab in Geneva. This is where, if you stand on the Jura Mountains, which is in France, and here are the Alps, this is Lake Geneva, this is not what you see. So you don't see that circle, that's just drawn in. The thing is underground. It is indicated here where various experiments with various names are. Here is the main site of CERN. Here is also the airport, so very close. And this is the Mont Blanc, so it's a nice location. And here is the cartoon of where the ring really lies. It lies underground at a depth of an average about 100 meters, not that close to the surface. And at various points in the ring, you have access points, and these elevators are fast. It's also the only elevator I know where the instruction is if there's a fire, take the elevator. In all other cases, when there's a fire, you don't take the elevator. Here, because there's little overpressure in the elevator, and it keeps the smoke out. So everything has been thought of. There were various sets of accelerators built sequentially in time, smaller ones older and then newer ones built later, and each is acting as a great example of recycling. Things you did experiments with before are now the pre-accelerators of the bigger one. So we'll see a little movie of that in just a moment. This ring, by the way, the circumference is 27 kilometers. So it's not small. And it goes, now the organization CERN is a large organization. There's 23 member states and about 10 has been done since the discovery. Well, the more solid work you have to do. You have to really consolidate what you know, stress test what of your understanding. So the accelerator and the detectors performed excellently. By now, there were 30 times more Higgses than in 2012. There will be lots more data coming, by the way. This is just a 10%, maybe less, of total amount of data that we will get from the LHC. So it will be still a lot more. The mass has now been measured to a very precise number of 0.1%. That's how accurate it is. The Higgs has been measured in a multitude of processes. So the Higgs has been measured directly. That's the discovery channel. Also together with two jet streams of particle. The Higgs together with a W or a Z boson, one of these force particles, with the top quark bit. So there's a lot of different ways in the Higgs has been produced. All of these things standard model can predict. So for all of these things, you can compare measurement and theory. See, do they all agree? Does one maybe not agree? And if they're different, the prediction and the measurement. And if the uncertainty in both is very small, you can say, actually, when you really look closely, there is no agreement and there is something new going on here. So it is worthwhile to stress test the understanding through accurate measurements and accurate calculations very, very much. This is also the theme of the Jan School. So that's what we do, stress test and take accurately measured but precisely calculated processes and compare them, see if there's any deviations. That's the general gist of what has happened. And in particular, this plot is important. I told you that the Higgs boson field in the background causes mass by equals to that Higgs field that's all around us. So if one particle is twice as heavy as the other particle, that is because the one particle feels the Higgs field twice as strong. There's a linear relation between mass and coupling. That is the way the mechanism works. And this is what they've been trying to see. So we measured the couplings of the top quark, the Z boson, the W boson, the bottom quark, and the tau. And they also measured the masses we knew, confirmation of the idea of the Higgs mechanism. If this would have been a curve, it would have been the wrong thing for us, for our understanding. This confirms again this strange Higgs mechanism as a way to give what it is. But we see it's indirectly there. It influences the behavior of galaxies and their rotation. We also see it influencing the early universe data. So we see it's there. We just don't know what it is. We're not even that sure it's a particle. But this one thing we know, it is not on the standard model. That we're absolutely sure. We checked. No standard model particle can act as dark matter. So it's new. Another question that's not explained by the standard model is why is there all matter? And we will not explain why planets, galaxies are all matter. We have never seen an antimatter galaxy or an anti-planet. So what happened along the way between the Big Bang and now? That's still a question that we cannot answer by the standard model. A more theoretical question is why the Higgs is so light. 126 in the units of particle physics. But really, if you look at the structure, it should be much, much heavier than that. Theorists say that, and since I'm a theorist, it's an absolute truth. Parody. So it is a theoretical problem why the Higgs is so light. It's called naturalness or fine-tuning. But we don't know why. The standard model itself provides no explanation. Maybe there are new symmetries involved. Notion of neutrino mass lies a bit outside the standard model. The early universe looks like it expanded in the very early fractions faster than light. It's called inflation. That's not explained by the standard model. Are the forces unified? These three forces, electromagnetic, strong, and weak nuclear force, do they become one early in the universe? Hints for that, I'll show you. We don't know. It's not in the standard model. Gravity is not in the standard model. Dark. This list is quite long, right? Still a lot to discover and to understand. And this is a nice picture I always like to show. Is there really unification going on? So this is a scale on which boson could help explain this. Why is it so light? Well, if there are other new particles that also influence the Higgs mass, and that you get from things like supersymmetry or other models, if you never heard of it, don't worry about it. But that would alleviate the problem. If that's the case, this is an indirect sign that there are such new laws of physics going around. In terms of inflation, there are models that try to argue that in fact this inflaton that causes the universe expansion in the very beginning is in fact the Higgs boson. So that's another option that is being looked at. And if these forces are indeed unified, then there should be a whole plethora of Higgs fields that comes with the model. So Higgs is involved in all these things beyond the standard. This three-point interaction is precisely related to the strange shape of the potential for the Higgs that caused the symmetry breaking. This was an assumption on our part. We assumed that this is the potential, and then from everything else followed. Now, the upgraded LHC, it's being upgraded now, may catch a first glimpse, but for the real measurement, we need a future collider. That comes me to the end. So beyond the LHC, what other colliders are we thinking of as a community? Well, we're used to very long-term planning. Things are expensive. There's a lot of R&D is necessary. The same as in astronomy, for example. You need to plan a long time. So here's a list of possibilities that are now being considered. A linear collider that collides electrons and positrons, not in a circle, but just as a straight line, linearly. And a possible location would be Japan, maybe even CERN if other options don't pop out. But there were preparations for for hosting this in Japan. It's not going all that fast, but there's colliders. You can hardly read it, but and you also see the years here. So we are now roughly here, 2020, but we're planning ahead to 2070. And this is also because things take a long time to build. You don't all have all that money in one go. So this is of course, schedule that will no doubt change. But you see the kind of planning that goes on. The way that goes on is that every 7 years, the CERN Council, in a 2-year-long, very intense process, updates its European strategy for particle physics. The present one was adopted in 2020, and it initiated a feasibility study into this possible future circular collider that goes here under Lake Geneva, if it ever gets built. Feasibility study means a lot. It's not just can you do it, can you make the tubes that go around, but you must find out, can you make the magnets that keep the particle going around? That's a big challenge. Where precisely do you locate it? Aspects. How do you deal with outreach? How do you make the project acceptable to the local community? The financial plan, how do you fund this? This is way more expensive than CERN can do. How do you fund this? All of that is part of this feasibility study. We're now in the middle of this to say go, no go on this. So that was it. That was the story. So what we've hopefully seen is that the discovery of the Higgs boson has truly started a new era in fundamental physics. And it confirmed a strange mechanism of getting a mass through broken symmetry. That's why it's so exciting to have this particle and this mechanism confirmed. And just by sheer existing, the Higgs boson, now that we know it exists, brought important new questions to the fore with realistic chances of answers. How do we go about them? Well, through very highly precise comparisons of theory and experiment, through worldwide collaboration, through CERN. Everyone have ear drum still? Yeah? So what ask at the top of that yeah. So very just yeah, so this is the potential for the Higgs field, and here you see this is the lowest place in the potential. And that's why it's a ground state in this picture. Universe, you need at least this thing for the mechanism to work. Now, what you're asking is, could there not further away be a point which is even deeper? Right, and this is indeed an option that people are looking at. That this is a metastable minimum, and that there's a deeper one. And classically, you cannot get there, but with quantum effects, you could get there. Now, what the that you can compute is how, suppose there is a minimum a bit deeper, a bit further away, could the Higgs field change into that? And if that would happen, we would all be in big trouble, because all the laws of physics would change. The likelihood of that happening, however, is not in millions of universe lifetimes. So we're safe.
So with people talk about the heat death of the universe.
No, this is not about thermodynamics. This is just about a stable one particle, one degree of freedom system, not statistics.
I have a similar question. You said it's too light, correct? The Higgs field.
It's
the Higgs boson.
The Higgs boson is by quantum effects considered unnaturally light, which looks a little unnatural. It's not wrong, it just looks unnatural. But if there would be other new particles, some supersymmetry or so, it would be much more natural. That's the idea. But other minima have not much to do with that.
Do you subscribe to string theory or new gravity?
I'm very agnostic about these things. It's not a matter of believing. It's a matter of working on it and see what it does. But maybe your neighbor has a chance.
Yeah. So during the application of Higgs boson, you said that did you imply that there might be different types of Higgs particles?
Yeah, there could be. If there would be a grand unified theory here, so if indeed the force in the universe.
Yeah. So the question was that in his book, The Elegant Universe, Brian Greene wrote that one of the possible predictions of string theory experimental verifications might come through LHC. So
that is pie in the sky. I think you're, well, is there anyone else perhaps? Yeah, over there.
Hello. So if there are other versions of Higgs boson, is it the constraint on the Higgs boson that the potential that you have shown must be followed by those variants or versions?
Yeah, so that depends a bit on the model. They all will get mass. None of them will be massless. That whole system of Higgs bosons will have a certain potential. So in certain popular cases, two Higgs doublet models or supersymmetric, there will be, in fact, two potentials, each of which with its own minimum, V1 and V2. And out of the combination, then you work out the consequences. And so it depends a bit on the situation.
Because all the masses of the particles that we have discovered, and we have experimentally confirmed, so they are based on that particular potential.
Yes. So the potential is input. That's is not based on previous experiments. So, but with that one idea, you can explain a lot. That's why it's so powerful. Yeah.
Is there abnormal invergence? Can Higgs Boson inverge in acidic?
I'm sorry, I didn't quite catch that.
Emergence.
Can the Higgs be an emergent particle? Is that what you're asking? So there's usually not. I'm sorry?
Structure formation in the universe.
Structure formation in the universe. Well, that's a bit. I don't know the answer. So in the early universe, of course, the into structures of galaxies. So that what we see in the universe as galaxies are really nothing but the remnants of small quantum fluctuations in the extremely early universe. Now, the Higgs boson is would have played a role in its very early quantum fluctuations and thereby have influenced perhaps the structure formation. I'm sorry, I have a hard time understanding with the noise. Okay, can you repeat the question perhaps?
Early models of a branch city conformal scalar field. Conformal scalar field.
The scalar field? What scalar field?
Can the Higgs field link to
the Brand-Sticker field? Is that what you're saying?
Conformal scalar field.
Oh, no, I don't think this. Well, maybe, but I'm not aware of that.
Sir, how magnitude of mass changes with difference in it?
Here. Oops. Here. So this is the process that led to the Higgs discovery. So these gluons here are like photons, also no mass. And these photons have no mass. And yet there is a Higgs particle in between. But you see there is no point interaction. It goes via this little loop here with a T. That's a top quark. The top quark is very heavy. So the way that this Higgs boson couples to these massless particles is not directly. That couldn't be. Otherwise the photons would have a mass, right? By the same reason you asked the question. So the way it happens here is that the Higgs boson couples to these very heavy top quarks. That's fine. They're very heavy. And the top quarks themselves couple to photons. So it's an indirect
discovery mechanisms. Do you consider history? Do you consider the prior findings, or what do you really refer to as?
which sorry, the prior, which early mechanisms? I didn't quite get.
While setting up the factors to find out how the universe was formed, which theories or which material do you refer to while forming such mechanisms, or while?
Oh, where does the mechanism as a whole come from even? Yeah, that we don't know, of course. The Big Bang is I always like this summary of the Big Bang. First, there was nothing, and then it exploded. Right?
Okay.
So that's what we know about the Big Bang. We don't know what happened before the Big Bang. We'll never know. So any theory is there as good as any others. It's just that this is the way the universe was created, and we work with what we find. But it's not possible to work back to what caused the Big Bang. Why do we have this Higgs mechanism in the first place? We can learn a bit more if we could, if there is a bigger theory than the standard model, and in that bigger theory, we could show that the Higgs potential, for example, has a normal shape with one minimum at some point, but as the universe cooled, it got this little bump in the middle. Right? That would be at least a bit of an explanation why we get this weird mechanism going. But for that, we would have to then know that theory with more particles and more symmetries. So you can understand more, but the very, very basic, we'll never know.
Also, I don't have a clear idea about how does it stand in this?
So in this story, it has no bearing. It is more.
In this.
I think there is no end to the questions.
So, how does we describe the field strength of Higgs boson field?
Sorry, where are you? There. Okay. Sorry, can you ask?
How we describe the field strength of Higgs boson field?
Which field?
Field strength of Higgs boson field.
I didn't catch the name. The Higgs.
The field strength.
Field strength.
Field strength. Yeah. The field strength of the Higgs.
Higgs boson field. Like in electrodynamics, we have electric field, like diverse, and electromagnetism it curls around. And in Higgs boson field, how we describe it in the form?
Well, so how does quantum field theory work is what you're asking, because all particles have their own fields. You have to think, how does quantum field theory work? That's a naughty cannot answer that in one question. It is a well-defined framework how to work with fields, the field for each particle, Higgs, up, electron, in a way that is consistent. And a particular quantum field theory is the standard model, and that is hangs together with symmetries and conditions and broken symmetries. So the fields are a natural ingredient of the standard model for whatever particle.
Can generating mass to the Higgs field be compared to Mach's principle for generating mass?
Can the mass of the Higgs field what?
What kind of mass is the Higgs field? Motion mass, gravitational mass?
The mass of the Higgs field so inertial and gravitational mass is the same for these particles. So the mass is both.
Can it relate to Mach's principle?
Sorry?
Can it relate to Mach's principle of generating mass? Mach's principle?
No, that's not in the standard model. I mean, it is the question is not answered by the standard model.
One last question. And, okay. You can ask the last question, and then we have the outside. You can ask the question.
Yeah. Right. No, it's massive. It's not zero. It's the magnetic field. The photons are the magnetic field inside the superconductor have a mass. Just like the W and Z bosons have a mass in our universe. So it's not zero, it's just extremely small. The resistance is absolutely zero, but not the magnetic field. Yeah.
So I think there are many more questions, and you are all welcome to accompany Professor Laenen for the last questions there.
Can I ask you a question? What is the score? India lost. Oh, I'm sorry. I'm very sorry. Yeah.
I would like to give a small vote of thanks. So we would like to thank the strategist, Vice Chancellor, Vice Chancellor, and for Laenen for arranging this talk. I would like to thank the CTAC's director and victory. Many thanks to my students, Vaibhav, Rav, and Namrata for helping me with organization. Thank you very much. You're all welcome for the office. And I would like to thank the speaker for a very good talk.
You're welcome.
And all of you audience for very lively discussion.